right, we'll continue with carbohydrates today. And the first thing I want you to know about carbohydrates is where the word comes from. So originally, it was discovered that there were certain molecules, when you purified them from organisms, that had a particular chemical formula. And for every carbon that was in the molecule, there was one oxygen and two hydrogens in that proportion. So one carbon, one oxygen, two hydrogens. And the original thought was every carbon has a water molecule attached to it. So two hydrogens, one oxygen, that's a water molecule. And there's one of those for each of the carbons. So it was considered these molecules must be just carbon atoms with water molecules floating around them, or hydrates of carbon. So we got the name carbohydrate. So the name comes from originally how the molecules were thought to be put together, and it originates from the chemical formula. For one carbon, there's one oxygen and two hydrogens. We know they're not put together that way, but the name stuck. They were still listed as carbohydrates, and they thought they were hydrates of carbon, but that's not exactly how they're put together. But the formula is correct. Okay, so they're composed completely of carbon, hydrogen, and oxygen in that ratio of 1 to 2 to 1. Right? A lot of context will give you an example of a carbohydrate at this point, and I don't want to do that and bias you, because they'll tell you that glucose is an example of a carbohydrate, and that's true, but it's not the only one by far. Right? And they like to tell you that it has 6 carbons and 12 hydrogens and 6 oxygens, but not all of them have that many carbons. Some have only 3, some have 8, some have 7, some have 4. So it varies quite a bit. So don't memorize any one formula except for the empirical formula, where there's 1 carbon, 1 oxygen, and 2 hydrogens in that ratio for simple carbohydrates. Okay, so another name for carbohydrate is sugar. Right, so we'll call them sugars as well. And another name for it in a different language this time would be a saccharide. Right, so carbohydrate, sugar, and saccharide all mean the same thing. They're all referring to the same molecules. Now we will use the words interchangeably, and sometimes we'll use them specifically to say it's a monosaccharide. And that means it's just a simple sugar. It can't be broken down into smaller, simpler sugars. Whereas if you have a disaccharide, you could call it a disugar if you want, or a dicarbohydrate. It means the same thing. We tend to use the word saccharide for that usage. But it just means that if you have a disaccharide, it's a sugar that can be broken down into 2 smaller monosaccharides. And those cannot be broken down any further and still be sugars. Right? You can move on past disaccharide. You could have something called an oligosaccharide. Oligo just means a few. Right? Doesn't necessarily mean 3 or 4 or 7, just a few of them. It's an indeterminate number. And then we move on past that into what we call polysaccharides. And poly could mean many. Right? In this context, a polysaccharide could be hundreds to thousands of sugars put together. Right? And those can be broken up into many, many monosaccharides. So that's what those terms mean. But looking back at the monosaccharides, or your simple sugars that follow that formula we talked about, they come in 2 flavors, right? There's the aldoses and the ketoses, okay? And by flavor, I don't mean they taste differently, although they do, but aldoses means that the functional group on the end of the molecule is an aldehyde, whereas a ketose means the priority functional group is a ketone. All the other carbons still have an oxygen on it. Remember the formula. For every carbon, there's an oxygen. So every carbon has an oxygen on it. Right? Every carbon doesn't necessarily have 2 hydrogens, but there are 2 hydrogens near every carbon. Right? And the way we say that is every carbon in this chain, except for the first one, or sometimes the second one if it's a ketone, so everyone except one will have an H on it and an OH on it. And that H and OH is where we got the misinterpretation that there was a water attached. It's not really attached as water. There's a hydrogen and there's a hydroxy on every carbon except one. One of them is either an aldehyde or a ketone. And of course its position in the chain determines if it's an aldehyde on number 1 or a ketone not on the end. And in all our cases, the ketones will be on number 2. Okay, so let's look at some examples of those. So at the top here is a group of aldoses. So if it's an aldehyde at the end, we call it an aldose. Ose ending generally means we have a sugar around, or a carbohydrate around. So the example here on the right, erythros, right, has an aldose at the top, right? It's got 4 total carbons. If you count up the number of oxygens, it will be 4. If you count up the number of hydrogens, it will be twice that number, or 8. Okay? So in every case of these sugars, they're all going to fit this formula for our simple sugars, our simple monosaccharides. At the bottom, we have an example of a ketose. This one happens to have 6 carbons, right? They can vary in their number, but it's still a sugar, right? It follows the pattern. For every carbon, there's an oxygen, right? 6 carbons there. There's 6 oxygens there, 1 on each of the carbons. And there's also 2 hydrogens for every carbon, right? So a total of 12 hydrogens. Of course, the carbonyl there doesn't have any hydrogens on it because there's only 4 bonds for carbon. But in total, the number of hydrogens is still 12 because the ends of the chain have an additional hydrogen, of course. Same goes with the aldose, right? There's a carbonyl on the end, of course, so that carbon can only have one other thing attached, 1 hydrogen. It can't have 2. And the other end of the chain, of course, since it's the end of the chain, has an additional hydrogen. Okay? But in addition to saying they're an aldose or a ketose, we need one more piece of information here. How many carbons does it have? So if it has 5 carbons, we'll call it a pentose. If it has 4 carbons, we'll call it a tetrose. If it has 6 carbons, it's a hexose. 3 carbons, triose, and so forth. All right, there are no 2 carbon sugars. So we'll follow this general pattern of naming how many carbons it has and whether it's an aldehyde or a ketone by saying aldose or ketose. So the example at the top again, erythros, it has 1, 2, 3, 4 carbons, so it's definitely a tetrose, and it's also an aldehyde, so it's an aldose. We put those prefixes together and we call it an aldotetrose. So it's an aldose 4-carbon sugar. That's what that means, right? It's an aldehyde containing 4-carbon sugar. Fructose at the bottom has 6 carbons. There's a ketone instead of an aldehyde, so it's a ketose. It's also a hexose. So we put those prefixes together and we get ketohexose. Right? This should be very simple to do with any number of carbons I give you, and it's either an aldehyde or a ketone. Okay, so let's practice on 2 of these. Right, so the one on the left, first thing we want to do is identify is it an aldehyde or a ketone at the end, and count how many carbons it has. So the one on the left, what would you call it, the total name?
Hexose?
Okay, so it has 6 carbons, I agree. What else do you need to know?
Aldohexose?
It's an aldohexose, exactly. Yeah, you need to know that it's an aldehyde as well. So the A on the left there is 6 carbons long, and there's an aldehyde group at the end, so it's an aldohexose. Okay, that's good. And the one on the right?
Ketose.
Ketopentose, yes. So it's 5 carbons, and there's a ketone group instead of an aldehyde this time. It'll always be on number 2 if it's a ketone. It'll always be on number 1 if it's an aldehyde, by definition. So this one's a ketopentose. Right? Whether you knew that it was allose and xylulose, it doesn't really matter at this point. I'm not going to make you memorize those. But you should know that you can determine its class or its type by counting carbons and identifying the aldehyde versus the ketone. That's what I want you to get so far. Okay, you don't have to memorize that that's allose and xylulose yet. I'll talk about which ones I want you to memorize. Okay. So let's do a very brief reminder on your least favorite word, or maybe your second least favorite word from organic, and that was what isomers were. Okay, and it includes your other least favorite word, which was chiral centers. So an isomer of something has, or any 2 things that are isomers, have the same molecular parts, same formula, right? They're just something different about them. If the thing that's different is the connection of the atoms, right? They differ in their attachments. The bonds arrangements are different. We call those constitutional isomers, and that's the box on the top left. Okay? It's a broad category of constitutional isomers. Okay? If you have the same parts, but they are connected exactly the same way, you don't necessarily have the identical molecule, right? It's not a constitutional isomer anymore. But you could have two molecules that have all the same parts, and they're connected, all the same connections, carbon to carbon, carbon to this oxygen, and so forth, but yet they're not the same molecule, and they differ in their stereochemistry. One example of that, not shown on the screen here, would be a cis versus trans arrangement. Okay? Everything's connected the same way. The same atoms are connected to the same partners, but there's a difference in the stereochemistry. Right? Another example of that would be an enantiomer. Right? You remember enantiomers? There's a chiral center. Right? There's one chiral center, and it's either a mirror image on one side and a mirror image on the other side, but they're non-superimposable. You can't put one on top of the other. The classic analogy for that is to look at your hands. Right? They are mirror images of each other. In order to make them superimposable, you'd have to turn one inside out to put it on top of each other because they don't match. There's definitely a left and a right. Same thing for these molecules with enantiomers. They're mirror images of each other. There's a plane of symmetry, but they cannot be superimposed. They're not identical. If they could be superimposed mirror images, then they are identical molecules, right? And that's not truly an enantiomer. Right? What you thought was a chiral center would not be that. The other type here we're going to talk about more commonly with sugars is diastereomers. Right? These are non-superimposable, not mirror images. Okay? They are isomers of each other because they contain the same parts. They're all connected in the same partnerships, the same bonds, but they're not the same molecules, and they're no longer mirror images. An easy way to do that is to have more than one chiral center. Okay? Enantiomers will only have one. So diastereomers, as the name implies, there are at least two stereocenters. Is a great way to think about it. So having two or more stereocenters, we're going to call those diastereomers. Right? They're still isomers. They have all the same parts. They have the same formula, but they're not the same molecule. Right? So if you look at the example shown here between aldose and glucose, they only differ in the second and third carbon positions. Everything else looks identical. Right? The aldehyde at the top, abbreviated CHO. Carbons number 1 and 2 differ in the position of the OH. Now on the screen, it looks like they're connected at 90-degree angles, which we know is not true. This is a Fisher projection, where the ones on the sides are either pointed towards us or away from us, and the ones above and below the carbon are, again, pointed away from us or towards us, respectively. So it's a stereocenter, it's a tetrahedral carbon. We just can't see it on a flat piece of paper. So here, left and right mean different things. So carbon number 2 on aldose, the OH is on the left, and carbon number 2 of glucose, the OH is on the right. The opposite is true for carbon number 3, glucose on the left, aldose has it on the right. And then for carbons 4, 5, they're both on the right, in the case of both sugars. And at the very bottom, carbon number 6 is not chiral because there's 2 H's on it, and it's the same for both of them. Just like carbon number 1 was not chiral. It doesn't have 4 single bonds. Okay, but aldose and glucose are still isomers of each other. They have the same formula, right? But they're not mirror images at all, and they're not superimposable, so they must be diastereomers. A subclass of diastereomers is where instead of differing at more than one of the chiral center, they do have more than one chiral center, but they differ in multiple places here. The other scenario I'm talking about is if they have multiple chiral centers, but they only differ at one of them. Okay, an example is the top right. These are called epimers, glucose and mannose. Glucose and mannose only differ at the first chiral center, carbon number 2. Right, so if you look at the top, there's the CHO for the aldehyde. Underneath is carbon number 2 for glucose. The OH is on the right. On mannose, we still have the aldehyde at the top, but carbon number 2, the OH is on the left. So they differ only in that position. From this point down, they're identical to each other. Okay, so these only differ at one of the chiral centers, but they do have more than one of them, so they're still diastereomers. But they only differ at one, so that makes them epimers. So that's the definition. They only differ at one of multiple places they could. Okay? And lastly, we have the final subcategory, and this one's a little more hard to understand, I think, because it's the same molecule. It's glucose in both cases. However, when this molecule goes from its straight chain form, which is shown in all these other pictures, to its ring form, right? You remember doing this from organic. I'll remind you again, where an aldehyde reacts with an alcohol to make a hemiacetal. We'll talk about it in a few minutes. You form a new chiral center when the ring forms. So the carbon number 1 here in the glucose was not chiral because it has a double bond. It's an aldehyde, right? But when it forms a ring form and interacts with the OH from carbon number 5, right? This is that new interaction here. We have a new chiral center. Carbon number 1 is now 4 single bonds. They're all different from each other. Therefore, it is a new chiral center. Okay? When that happens, it could adopt the form where the OH was pointed down or the OH pointed up. We'll call the one where it's down alpha and the one where it's pointed up beta. They're both still D-glucose, but we have 2 forms of it, and those are called anomers of each other. Just like it sounds, they're the same name, but they're truly not the same molecule, right? They're slightly different, so they are isomers of each other. We call them anomers. They're still diastereomers, and they're still stereoisomers. So let's look closely at this Fischer projection to remind you what I'm talking about. So at the example on the bottom is our smallest chiral sugar with only 3 carbons in it. So we have glyceraldehyde in its L form on the left and its D form on the right. Right? And what do we mean by that? So I'm saying L because the OH is to my left, and D because the OH is to my right in this Fischer projection. Okay, what does this really mean? So it means I put the highest oxidized group at the top. That's going to be my aldehyde here, and then everyone else listed down below. And then to the left and right of each chiral center, there's only one chiral center in this whole molecule, carbon 2. 1 and 3 are not chiral. The OH could be left or right, and this determines my L or D status. Okay? So the OH here on the left and the H that's pointed to the right in L-glyceraldehyde are both pointing towards me out of the plane of the board, right? And the aldehyde group above and the CH2OH group below are both fading into the board as dashed lines, right? So these would be wedges left and right coming at me, and dashed lines above and below if you want to look at it in the true stereochemistry. Right? On the right, we have the exact same thing. The above and below lines should be fading away, and the OH to the right and the H to the left should be coming towards me. So if you imagine the molecule on the left, the L-glyceraldehyde, in those 3-dimensional assignments where the sides are coming towards you and the top and bottom are fading away, pointed away from you, and turning the molecule around in your mind, just turn it around 180 degrees, such that this OH ends up on the right, this H comes around to the back, right? These just turn around. They're not chiral, they just spin. But this one was pointed back. It'll now be pointed forward, right? And this one will also be pointed forward. These two would then be pointed away from me. And that has the orientation of this molecule, right? With the OH is on the right, the H is on the left. But the chirality in the center is exactly the opposite. Things are pointed in the opposite directions as what we described on the right. And there's no way to rotate that molecule to make it fit over the other one. So they are not the same. Right? So the only way to make one fit over the other exactly would be to swap any 2 of the 4 attachments to that chiral carbon. And if I swap them a second time, I'm back where I started. Any 2 I'd like. So to use the Fischer projection, we're going to look at the sugars in this arrangement where we put the highest oxidized group at the top, our aldehyde here, or in the case of our ketones, we're going to put the ketones number 2 near the top. Number 1 will be just above it. And then we line them up down the center. OH is to the left and right like you just saw. Okay, so here's some examples of those. At the bottom here I have 3 molecules, glucose, ribose, and galactose. Okay? The glucose on the far left has how many total chiral centers? So this molecule on the left has how many chiral carbons?
4.
4. Right, the first one is not chiral because it's got a double bond. Right, the last one is not chiral because there aren't 4 different things attached. There's 2 hydrogens on it here. And the 4 in the center each have 4 different things attached. So go through that as an exercise on your own and make sure that you agree that there are 4 different things attached here. I don't mean look at the immediate atom, because yes, there's two carbons attached, but this is a one carbon group attached up here, and this is a much larger group attached down here. They are not the same groups, and neither is the same as the H or the OH. So yes, there's 4 different things attached at each of these places. Right? How about the one in the middle, the ribose? How many chiral centers does it have?
3.
3. Again, we can exclude the first one, and we can exclude the last one, so only 3. And then galactose on the right, again, just like glucose, will have 4. We can exclude the first one because there's double bond. We can exclude the last one because it doesn't have 4 unique attachments. The 4 in the middle are, again, chiral. When I decide if it's an L or D sugar, and it has more than one chiral center, unlike our friend up here at the top only had the one, it was pretty easy to decide. When I have more than one, how do I decide? Well, I look at the next to last carbon, or the penultimate carbon, or another way to say it is the very last chiral center, because the last one will never be chiral, right? It's always a CH2OH. So the last chiral center, or the penultimate carbon, the next to last carbon, will determine its L or D status. So if it's on the right, the OH, we're going to call it D. If it's on the right, D. It's on the left, L. Right? No matter where the others are, the last chiral carbon's OH determines the L or D status. Okay? The others fall where they may. And when you look at this one happens to be glucose. If I leave this alone, it's still D-glucose, but if I rearrange the OHs in these 3 carbons, it's no longer glucose, but it'd still be D if I leave this one alone. Okay? So the last chiral center, look left or right, determines if it's L or D. So what's the significance of this L or D? Why do we like to use this in biochemistry and not E or Z or R or S type of assignments? Because it has physical meaning, right? L and D have a physical meaning that goes back to how it rotates plain polarized light in a tube. So if you take a solution of any of these molecules, as long as it's a pure compound, like all D-glucose or all L-ribose or something, and no matter what it is, as long as it's just a pure solution of that and nothing else in there, and I shine plain polarized light through it, which means I have some light source, which the light's going in all different directions. I run it through a polarizer. You can use a sunglass lens for this if you'd like, because most of them are polarizers now, right? So the light's all in the same plane, right? And if there were nothing in the center, and I put an observer over here, and you took another lens and lined it up with this polarizer, right? The light would come right through, no problem. But if you take 2 sunglass lenses, you can do this on your own. Just don't look at the sun when you're doing it. Just look at a light bulb or something. You take 2 sunglass lenses, or 2 pairs of sunglasses that you can put on top of each other, and you turn one 90 degrees to the other, you will not see the light at all, because you've blocked out all the light by being orthogonal to the other. If you line them up directly, the light gets the brightest. However, if you pass that light from one lens before it goes through the other, it will rotate the polarization of that light. That's what these molecules do. If they're all D or all L, right? They'll rotate the plane of polarized light. So it rotates through a certain angle that's specific for that molecule. You'd have to turn your second lens so you can see the light again, right? And if it rotates it to the right, we call that a D isomer. If it rotates it to the left, we call it an L isomer. And in sugars, the last chiral center is responsible for this direction of rotation. So that's why we use that to describe it as D or L. That's where the name comes from. So as an example at the bottom, are these 3 sugars D or L sugars? So how about the first one? Is this a D or an L ribose?
L.
L, because the last chiral center's OH, right, is to the left. Right? Number 5 here of ribose is neither left nor right. It's not chiral. Okay? So don't always think it's number 5. This one has 5 carbons, so it's the next to last carbon, or number 4. Right? Threose, is this one a D or an L threose?
L.
L again, because this last chiral center is to the left. And then fructose on the right, again, we put the highest priority at the top, meaning it's a ketone, so number 2 here is near the top. Is this D or L? Is the fructose a D or an L sugar?
D.
D. And we're not looking up here, not because this is on the right, because we go to the last chiral center again and look to the right, there's the OH. Had this OH been on the left, it would have been an L fructose. And in fact, the whole molecule will be turned around. Okay, good. All right, so here's the sugars I want you to know. You don't have to memorize this entire list. I picked out 4 here on this huge list that I want you to know. But let's look at the list as a whole first. Every sugar in this list is a D sugar, right? You could make an identical list on all of these being L, right? So there are equal number of L counterparts to these D sugars. However, in nature, we generally see nothing but D sugars. There's the rare exception, but for what we're going to talk about is mostly D sugars, right? So there is an L version of this chart, and you don't have to memorize it because it looks almost identical to this one, just everything turned around. But I want you to know 4 of these D sugars. And the simplest one at the top, the D-glyceraldehyde. Okay, so it's only got 3 carbons. There is but a single chiral center, right? And of course, it's the last chiral center if it's the only one. So with 3 carbons, it's the last chiral center, number 2. It's on the right, as all of these are. It's D. Okay, so a very, very simple sugar. Aldehyde at the top, right? The OH on the right, and then they all end in CH2OH on their last carbon. So very, very simple, basic construction for a sugar, D-glyceraldehyde. And if you go down to the next row, with the 4 carbon sugars, right, the tetroses, there's erythrose and threose, but you don't need to memorize those. Just see how we're adding 1 more carbon, and every time I add a new chiral center, I double my options, right? So in the erythrose, they're both on the right. In the threose, it's the left, right. Okay, the last chiral center for everything on this chart will be on the right because it's D. If I add a 5th carbon, then each of these has 2 more possibilities. So there's a grand total of 4 options with 5 carbons. There's ribose, arabinose, xylulose, and lysose. You don't have to memorize all those. I want you to know ribose. Why? Because it's a relatively important sugar in biology, right? This is the sugar that's used in the backbone of your RNA molecules. Okay?
Dr. Meats, I have a quick question.
Yeah.
Is the D-erythrose and D-threose, are those considered epimers?
So those are considered first isomers, right? Because they have the same formula. Then we'll go down the chart and say they are diastereomers because they have 2 chiral centers, right? They're not mirror images or non-superimposable mirror images at all. And then are they epimers? Do they differ only at one of their chiral centers? Yes. So I would call those epimers as well. Are they anomers of each other? No. Anomers is when you fold it into its ring form to make 2 versions of the sugar. So you're absolutely right. They're isomers, they're stereoisomers, they're diastereomers, and most specifically, they'd be called epimers.
Thank you, Dr. Meats.
So, and we can say the same thing for most things in this chart, where if you look at any 2 next to one another, they're only differing by 1 chiral center. So pick any 2 next to each other, like at the bottom, galactose and talose, only differ by their first chiral center. So again, they would be epimers. However, galactose and let's say glucose over here differ in more than 1 chiral center. Or do they? No, they still differ in 1. You get the idea. Mannose, for example. Right, so moving on to the 5 carbons here, I want you to know ribose. Of the 4, it's the only arrangement where all the OHs are on the right. Okay, it's very easy to remember because it's ribose. So in ribose, D-ribose, all the OHs are on the right. Okay, very easy to remember. Okay. The other one I want you to know are in the 6 carbon sugar groups. And that's the most common ones here, which would be glucose and galactose. Well, really only have to memorize glucose because galactose is 1 thought away from glucose. So if you memorize glucose, like ribose, most of them are on the right, but number 3 is not. It's the only one that isn't. All the ones on the right are called allose or allose, right? They're all on the right. So here we have right, left, right, right. If you want to remember it like marching, you can do that, or remember they're all on the right except number 3. They're all on the right except the 2nd chiral carbons, OH. However you want to memorize it, you have to know glucose. Once you have glucose memorized, and by far that's the most important thing you need to get out of today, is learn how to draw glucose before anything else. If you want to draw galactose now, just remember that galactose is change number 4 from glucose. That's it. Everything else is the same. So here's your 4 carbons. It's right, left, right, right. Except in galactose, we change number 4 to the left, so it's right, left, left, right. It's a very weird march. Okay, so glucose and galactose know those. Ribose, 5 carbons, all 3 OHs on the right. And the simplest aldehyde sugar, glyceraldehyde, with its OH on the right. Okay? So know those 4 D-aldehyde sugars, or aldoses. If I do this for the ketoses, the chart is much smaller. In fact, it's half the size. The reason being is our 3-carbon sugar, that's a ketose, has no chiral centers. It's neither left nor right, neither D nor L, because there is no chiral center. The reason being, we know the last carbon is never chiral, it's CH2OH. In the case of a ketone, though, or ketose, carbon number 2 is where the carbonyl is, instead of carbon number 1 on the aldehyde. So number 2 can't be chiral, and because this is now on the end, it also can't be chiral. It's got 2 hydrogens. So the first, second, and last, in that case that's the only 3, can't be chiral. So there are no D and L versions for a 3-carbon ketose. When we move on to the 4-carbon version, there's only 1 chiral center again. Again, the first, second, and last can't be chiral. So only 1 chiral center for this ketose. Right? Don't have to memorize that one, just get the idea this is the simplest up here at the top. Okay, it's neither D nor L. If I add another carbon, again I double my options, but it's half the size of the previous chart. Right? And I have ribulose and xylulose. Right? These look a lot like the other versions where both are on the right, and then we have left, right. This looks almost like ribose. In fact, it's a cousin of ribose. The only difference between ribulose and ribose, slight difference in spelling of their name, is that this one's the ketone version of ribose. If this ketone instead were an aldehyde up here, and this OH on the right, it would be ribose. Okay, so ribulose is the ketone cousin of ribose. Okay? And we can play the same game for our 6-carbon sugars. Fructose is the ketone version of glucose. Right, so here we have carbon 1 not chiral, carbon 2 not chiral, last carbon not chiral. But from number 3, 4, 5, 6 on down, it looks exactly like glucose. So glucose, this would normally be on the right if there were a chiral center at 2. Then left, right, right. So fructose is the ketone cousin of glucose. Ribulose is the ketone version of ribose. And of course, D-erythrose is kind of unique. It's the only 4-carbon ketone sugar with only 1 chiral center. There is no other option, as we had with the aldehydes. Okay, so I want you to know the glyceraldehyde, ribose, glucose, and galactose is only 1 away from glucose in the aldehyde chart. And I want you to know dihydroxyacetone, which is the simplest ketose, and the cousins of ribose and glucose, ribulose and fructose. Okay, so really learning these is learning one, and the others are just a thought away or a change away. It's very simple. But learn glucose first. Okay, so back to what you learned in organic, and this is going to be our how we get anomers, or getting a new chiral center by the molecule interacting with itself. If you have an aldehyde reacting with an alcohol, they form a hemiacetal. There's a rearrangement where the alcohol's O attacks the carbonyl. This carbonyl becomes an O-, grabs the proton and becomes OH, and we make a hemiacetal. This carbon, which was not chiral before, is chiral now. 4 different groups on it, right? So it went from a trigonal planar geometry to a tetrahedral geometry and is now a chiral center. In the case of sugars, the aldehyde is the first carbon. The alcohol I'm talking about isn't a separate molecule. It's part of the same molecule. So when this alcohol group interacts with the carbonyl, I'm not forming just a new bond as shown here. I'm forming a new bond that closes a ring, right? So the OH on number 5 here interacts with the aldehyde up here, right? It's better going around this way, right? So this OH interacts with this aldehyde here, and this becomes a new OH, right? And that OH is on a new chiral center at number 1. It could be pointed down, we'll call it alpha. Could be pointed up, we'll call it beta, right? Both of these are still glucose because they still have the same arrangement. Carbon number 2, 3, 4, and 5 were right, left, right, right. It's still right, left, right, right, right? And what do I mean by that in this ring form? How do you know it's right or left? It looks like it's up and down. That's why I drew this OH attacking from the left. Imagine this straight chain molecule in its Fischer projection, right? This OH is kicking itself in the back of the head basically, and the whole molecule falls down to the right. Okay, that's kind of what's shown here. This whole molecule, it's reached around and kicked itself in the back of the head and it's fallen over to the right. So if you're pointed to the right and the whole molecule falls over, you're now pointed down. If you're pointed to the left and the whole molecule falls over, you'd be pointed up. So that's why number 2, which is to the right, is now down. Number 3, which is left, is now up. 4 is right, it's pointed down. Number 5 is still pointed to the right. It's in the ring now. It's pointed to the right. Okay? Number 6 was not chiral before, and it's not chiral afterwards. Number 1 was not chiral before because it was involved in a double bond, but it is now chiral and it can exist in one of 2 forms, either the alpha or beta forms. We tend to refer the straight chain glucose as just glucose, or open chain or straight chain glucose. But to distinguish the one it's in its more stable ring form, we have to give it a new name. We don't just call it glucose anymore. We'll call it glucopyranose. The pyranose refers to the shape this molecule takes, right? It kind of resembles a pyran ring. It is not pyran, there are no double bonds in it, but it resembles a heterocyclic ring of 5 carbons and 1 oxygen, and that's kind of what we have now. And the geometry is not the same as pyran, but if I say glucopyranose, it means a sugar, glucose, that looks like pyran. It's in its ring form is all we need. If you just say plain old glucose, you probably mean the straight chain. We often just say glucose for both, but if you hear pyranose or glucopyranose, it definitely refers to the ring form. It doesn't mean it's equal to pyran, that's just how it resembles. If we play the same game that we did at the top, but instead of starting with an aldehyde, we start with a ketone, we form a hemiketals, right? The only difference here is this R group, right? It was a hydrogen before, and it's not involved in the chemistry at all. It's not a hydrogen afterwards. But we still get a new bond made and a new chiral center made, and all the chemistry is identical. Okay, so in the case of fructose, so we have 1, 2, 3, 4, 5, 6 carbons again. It's going to kick itself. Instead of in the head this time, the carbonyl is kind of at its shoulder. So it reaches around and kicks itself in the shoulder. The molecule falls over to the right one more time. However, the ring is smaller because instead of this O attacking carbon 1, it's attacking carbon 2. So we get a smaller ring by 1 member. So here we're going to make a 5-membered ring instead of a 6-membered ring. And when it forms this OC bond here, we're making a new bond, just like the OC up here, right? This carbonyl becomes a new chiral center. And it could be pointed up or down again. If the OH is pointed down, once again, we'll call it alpha. If the OH had been pointed up, we're going to call it beta, right? But everything else still applies. Number 3 was to the left, so number 3 is pointed up. But keep in mind, position of number 2 is here on the edge. Number 3 is right here, right? Number 4 is to the right, so it's down. Number 5 is still to the right because it's in the ring. And number 6 is still not chiral. Some other ways of visualizing that. We have our Fischer projection on the top left, like we've been looking at. We could make it in this Fischer ring form, which was an attempt to show you that carbon number 5's OH is the one forming the bond. These are not additional carbons, right? But it's not a very pleasing form. It looks like there are 3 additional bonds in there. Or we do the Haworth projection, which is a better way of representing it, where if down and up definitely don't mean down and up, because these are still tetrahedral centers. But what they mean is on one face of the ring or on the other face, kind of like hemispheres, right? Think of the plane of the ring is not truly in a plane. You know it's in the the chair or boat conformation, but you can imagine it as a region. There's an above and below the ring region. So it's either in the southern or northern hemisphere. Right? So down, we'll say, is below the face of the ring, and up is above the face of the ring. And this is glucose again in this form. So here we have it down, so this is an alpha glucose. Number 2 is down, number 3 is up, number 4 is down, number 5 is to the right still, 6 is still not chiral. Right, so this is definitely glucose, and glucose with this arrangement, all the OHs are as far from each other as possible, making it the most stable sugar and the most soluble of the sugars. This is why glucose is so prominent. If you want a better visual of that, you can look at this projection at the bottom, showing the OHs and their axial or equatorial arrangements, and they're as far away from each other as they can get. So what's some properties of this glucose molecule? Well, it is an aldehyde, and as you remember from organic, aldehydes are quite reactive. Right? They can either be oxidized to a carboxylic acid, or they could be reduced to a primary alcohol rather easily. So a way to test for sugars is to test for a reducing sugar. Is it an aldose? Right? So if it's an aldose, it exists either in its ring form with the hemiacetal, or in its straight chain form, and those are back and forth all the time. It spends the majority of its time in the ring form, of course, because it's more stabilized. But it does exist in the straight chain form, so there is a reactive aldehyde present occasionally. And if you react this with something that could oxidize it, right, the aldehyde to a carboxylic acid, and in the process it becomes reduced itself, it'll react. So in this case, we add it to a copper solution with a divalent copper atom, +2. It'll oxidize the carboxylic acid, right, the aldehyde to a carboxylic acid. And in the process, it's accepting those electrons and turning the copper +2 into copper +1. Right? So copper +1 is very reactive. It reacts with water and the hydroxides in solution to become a copper oxide. It's a brick red precipitate, right? And it falls out of solution. So we see a nice blue cupric ion in solution. We never truly see the green cuprous ion because it reacts with the water right away, and it turns brick red. So if you take this copper solution in blue and you add a solution to it, a sugar solution, you're asking, is it a reducing sugar? If it turns brick red, then yes, that was a reducing sugar. It was most likely an aldehyde. So my question to you is, would a solution of fructose undergo this reaction? What do you think?
No, because fructose is a ketose.
So you're absolutely right. Fructose is a ketose, and it should not undergo this reaction because ketoses or ketones can't be oxidized. I agree. However, if you take a solution of fructose and you add it to this copper solution, or just mix in the copper with it, it will turn brick red. Anybody think of an explanation why? And it's not contaminated with glucose. I started with a pure fructose solution. And this is true for any monosaccharide, whether it's a ketose or an aldose. It will show this reaction. It will turn this brick red. The aldoses will do it immediately. The ketoses take a little longer. There's a delay, but it will turn brick red eventually. Anybody have a suggestion why? So the reason, if you think back to when we were describing these sugars, I said fructose was the ketone version of glucose. And in fact, every sugar there, every aldose there had a ketone version of itself on the next page. And the conversion from one to the other is rather simple. You just move the carbonyl from carbon 1 to carbon 2, right? So that's all I need to do. So on the left here, I have a representation of glucose where I'm not showing carbons 3 through 6, I'm just representing it by an R in the diagram. But carbons 1 or 2 are the aldehyde at the top, and then carbon number 2 is OH on the right. On the very right-hand side of this picture is fructose, represented the same way, because carbons 3 through 6 in fructose are identical to glucose. Nothing's changed. But carbons 1 and 2 are quite different. So carbon 1 is the CH2OH, and carbon 2 is my ketone, making it the ketose. There is an intermediate between the two. In glucose to fructose or fructose to glucose conversion, we have what's called an enediol in between, because what happens is the carbon-carbon interaction here gets a double bond, and the carbon bonds to each of its oxygens are single bonded. So instead of having a ketone or an aldehyde, I have a diol, right, two OH groups that are bridged by a carbon-carbon double bond, or an alkene. So it's called an enediol. Right? So this is not as stable as the other two arrangements, because the double bond, being the oxygen being more electronegative, would love to have the double bond to itself rather than between the carbons, but it does exist. So if you ask which of these three is the least stable among them, it's the middle one. But it's not terribly unstable, right? There's nothing crazy about it. So glucose could spend some of its time as the enediol form and spend most of its time as just glucose, right? And this would wrap up into its circular form, right, or its ring form. But in the straight chain form, it could sometimes look like this. Occasionally, when it turns into this, it could also, instead of resolving itself this way, could resolve itself as the fructose molecule, which would then cyclize into its ring form. Okay? So this middle molecule is a slight bump, if you think of it, in terms of energy between the two. But if you have the solution, say, warm enough, right, not really cold, the glucose or the fructose could turn into the other form. So if I have a solution of pure fructose there, right, and I warm it up a little bit, or let it sit for a long enough time, eventually some of it will turn into glucose, right? Most of it will still be fructose, but some of it will turn into glucose. And if I have a solution of pure glucose, I can say the same thing. Some of it will turn into fructose. Okay, so this is why, on the previous slide, we have this reaction very rapid with glucose, but if I put a solution of fructose in here and expose it to this copper, it will also turn red, because some of it, even though it's a very small proportion, does exist as glucose in solution. And as soon as that glucose turns into the carboxylic acid here, right, it'll be replaced by more. This is Le Chatelier's principle. As I remove some of the glucose in solution, that's a very small proportion that's there, it'll be replaced by more, right? Conversion into glucose. And that reaction proceeds until all of it turns into this brick red copper oxide, and all of it's in the carboxylic acid form. But that's a slow conversion unless I heat it up. If I raise the temperature, this will occur more rapidly, such as boiling the solution, right? You'll get the fructose reacting almost as quickly as the aldehyde. Okay? So it's also the reason why if you take a jar of pure honey, which is almost pure glucose, and you heat it up, or you try to cook with it, and you let it warm up, and then you cool it off again, it's not going to be honey anymore, right? It won't stay as a fluid anymore. It crystallizes over time, because a lot of the glucose is turning into fructose. So if you want to buy a jar of honey, or a container of honey, whether it has a bear shape or not, but you have a container of honey, don't buy them in huge quantities, unless you plan to use a lot of it very quickly, because over time, some of it will convert to fructose, and it will crystallize in your cabinet. Okay, so buy some. Go ahead.
Dr. Mead, so for the enediol, is that specific to glucose fructose interconversion, or can you use that for all aldose?
Right. This is for all aldose to ketose conversions, where R is just common between the two. The example I'm using is glucose to fructose, but if R is the same, whether it's 1, 2, 3 carbons or so forth, this is still the same idea. Like ribose to ribulose will do the same thing.
Okay.
Good question. I'm just using glucose to fructose as the example because we commonly see it in tests and in such like honey and things like that.
Excuse me. So they need to be cousins for this to happen?
Right. So if the only thing changing here is at the top of the molecule, the R remains unchanged. So you can't turn a glucose into let's say a ribose into a fructose. Number one, they don't have the same number of carbons. And number two, they don't look the same below that point. So it has to be the cousin ones we're talking about. They don't convert into other sugars. Does that make sense?
Yes,
Right.
thank you.
This doesn't change the number of carbons, and this doesn't change any features of the R group. It is what it is. It's not involved. Okay, but this leads to another conclusion. If I go back and ask you which sugars are reducing sugars, the answer is all monosaccharides can behave as reducing sugars, even the ketose versions, because they have an aldose cousin that they could turn into. Right now, if you keep them frozen at liquid nitrogen temperatures, the chance of it converting to its aldose cousin and reacting is very, very small. But at room temperature or higher temperatures, that chance is non-zero. So you will get a reaction, you will get this brick red product, right? Or if you do it with the Tollens test with the silver mirrors, the same type of test, just uses silver instead of copper. But it will test positive. All monosaccharides will test positive. The ketoses reacting slightly more slowly because they have to convert to their aldehyde forms. Okay. Let's look at some other reactions that these sugars can do. So at the top here, we have our alpha D glucose. Let's make sure we understand where that comes from. It is glucose, and I got to confirm that by saying carbon number 2 is down, which is right. Carbon 3 is up, which is left. Carbon 4 is down, which is right. So we have right, left, right. That's glucose. There's 6 total carbons. Number 6 is again sticking off the ring, not involved. And number 1 happens to be pointed down because it's in its ring form. This is the glucopyranose form, right? So O pointing down, we're going to call it alpha. We could have had beta, but in this case, it's just alpha. Okay, so we identified the molecule. We're going to react it with an alcohol like methanol, very simple alcohol. And if you remember, this carbon number 1 is a hemiacetal. When you react a hemiacetal with another alcohol, you form a full acetal, right? And of course, you get water as a byproduct. So the H here leaves, this O attacks this, carbon. We form a new carbon-carbon bond, right? Or sorry, carbon-oxygen bond, right? And then this O and OH leave as water as a byproduct. Okay, so this carbon is now a full acetal. There's 2 OR groups on it. It still has the original other 2 connections. There's an H still on here, so it's not a ketal, it's an acetal. And we've attached this carbon, basically, to this oxygen. Okay, so it's just like you did in organic. When you take an aldehyde and react it with an alcohol, you made a hemiacetal. When you added another alcohol, you made a full acetal. Whereas the first case here, it's reacting with its own tail, right, forming the cyclic version. And then we add the second alcohol and we put this new carbon group on the oxygen. Now, once I've done this, this ring is fused shut, right? There's no OH here that can deprotonate like this one could on the left, deprotonate and go back to its straight chain form and form a carbonyl. You're not going to demethylate very easily, right? So this is no longer able to open into its ring chain, right? And it would no longer be considered a reducing sugar. There's no available aldehyde anymore. So if we methylate this glucose, we can make it not react in that reaction. Okay? So all I did was add some alcohol. We end up putting the remainder of the alcohol minus its OH on this O. Let's do the same reaction again, but in this case, instead of putting a simple alcohol here, let's use another glucose molecule. Okay? So here on the left, again, we have our alpha D glucose, and here on the right, we just have another alpha D glucose. How do I know it's alpha D glucose? Let's check again. So carbon number 2 is down, right, which means it's to the right. Carbon number 3 is up, so it's to the left. Carbon number 4 is down, so it's to the right. And then carbon number 1 happened to be down again, so we'll call it alpha. That's not relevant to this reaction, but it could have been up or down. We'll ignore that for a minute. On the left here, This one happens to be down. We'll call that one alpha as well. This one could have been either case, and this one could have been either case. This is just the example I'm using. So this sugar is going to act just like it did at the front, at the top here. This H is going to leave. They've miscolored them here for you. This H is going to leave. This O is going to stay. This should be a black O, right? And this O, I'm sorry, they miscolored it at the top. This OH is leaving along with this H. That's correct. And this O here is just like this alcohols here, right? Will get attached at this carbon. So instead of attaching just a methyl group, I'm attaching an entire sugar onto this O. And that's shown here on the right, where this entire sugar is attached through this oxygen now. So if you want to correct this figure, we should correct it at the top. This O should be red and this one black. Okay, so the OH on the sugar at the top should be red, and the methyl group next to the OH and the methanol should have a black O. If we want to correct that top figure. Eventually I'll correct them in the slides. What we've done is locked this first sugar into its ring form. Just like above, I said it can no longer open into a straight chain. This first sugar at the bottom can no longer open. There's no OH. However, the second half, the second sugar, can still open and close all day. Right? So it might be alpha at the moment, but this one can open and close on the right, no problems. But the connection between the two is fixed. Right? We cannot open the middle, the first ring anymore. This is called an alpha glycosidic bond because the first sugar that was involved, its alpha number 1 carbon got involved. Whether the second sugar was alpha or beta was irrelevant because that carbon was not involved. Carbon number 4 on the second sugar was involved. 1, 2, 3, 4. So we call this an alpha 1,4 glycosidic bond. Okay? So both of these reactions, the one at the top and the second one, are what kind of chemistry? If you had to put an enzyme class to this, what type of enzyme would accomplish this? One of your 6 classes you learned.
Would it be a ligase?
It would not be a ligase. Look at the top one. That'll help you figure it out. The bottom one can confuse you and make you think it's a ligase.
Yeah, I was looking at that one. Would it be a ligase?
So look at the top one. I have, now we gotta fix these colors up here, of course, but we have a CH3, right, that's getting attached to another oxygen, right? And it's kind of losing part of itself. And it's easier to see in the bottom as well. This sugar, which would normally be attached to something else, which we'll see later when we get to metabolism, is losing its attachment and getting attached to something else. These are examples, if enzymes catalyze these things, they would be transferases. It's taking it away from something, giving it to something else. I know the full picture is not here because we're not doing metabolism yet, but a methanol and this glucose normally would not interact with each other in solution. I mean, they wouldn't react in this way. You see, we're having to raise or lower the pH and add some catalyst for this to happen. But if you did this for a function of an enzyme, these would be attached to other things, like the methyl group or the sugar would be attached to something else, and the piece I'd like to connect would get transferred onto there. Same thing at the bottom. If I want to transfer this sugar onto another sugar, there must have been a group that left as a leaving group, right? Not just water. Okay. I know these are hard to see in the moment because I'm not showing you the enzymes and the activated molecules, like the uracils and the UDPs that would be leaving here, but we'll talk about it later when we get to metabolism. Okay. Here's an easier one for you at the top. Let's take our disaccharide we just made, add some water, and break the bond we just made. Right? So if we add water and break this bond, right? Again, they got their colors mixed up here. But we break this bond, right? And I'm left with 2 individual glucoses. Now both of them are free to open and close once again. Not the fact that this is water, that doesn't make it hydrolysis. The fact that I'm adding a small molecule and breaking a single bond into separate pieces, that's what makes it hydrolysis. Water happens to be the most common thing you add to do that. Okay, so this would be a hydrolysis reaction, not simply because there's a water molecule there, don't think of that, but because a small molecule, water is a great example, is breaking a single bond. That's the reason it's hydrolysis. Okay. The one at the bottom is much like the other two on the previous page. I have a glucose molecule once again. This one happens to be beta glucose. Could have been alpha, but happens to be beta. It doesn't really matter in this case. And I'm adding something to carbon number 6. Right? So the carbon number 6 is getting a phosphate put on it. The donor of that phosphate is an ATP molecule. So the ATP with 3 phosphates is donating 1 to the sugar, leaving 2 behind. Right? And this is done by the enzyme hexokinase. What kind of enzyme is hexokinase? What class?
Trans.
Again, this would be a transferase, right? I'm taking the phosphate away from this thing and giving it to the glucose, right? Leaving just 2 behind. Okay, and now I have a glucose with a phosphate on it. Happens to be at number 6. And we'll talk about that when we get to metabolism as well, when we do glycolysis. Okay. So some other names here. You have some other various sugars on the page here. They're not just glucose. We have others in that big chart. I don't want you to memorize these new ones. They're just examples of what can be done to sugars. Whenever you see the normal sugar, like this one here, right, the one in the center here, where it says it's a green beta arrow, right, either one of them, right, and you count around carbons 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. 6 is generally pointed up off the ring, right? But when it's an L sugar, these were D sugars. When it's an L sugar, you count 1, 2, 3, 4, 5, 6 is pointed below the ring. Okay, it's not in the middle of this ring structure. It's not what this means. Remember, up and down mean above or below the face of the ring. So in the case of fucose on the left, the methyl group is pointed down, whereas number 6 is pointed up if it's beta. Or if it's D, sorry. If it's alpha or beta, that is determined by the first carbon, or in the case of ketoses, the second carbon, whether it's up being beta or down being alpha. Okay. Now I know the one on the left, you might be thinking, hey, you just said pointed down is alpha. That's true. But when it's an L sugar, everything is inverted. Okay, so pointed down for number 6 means it's L, right? Because number 5 is no longer to the right. It would be left if drawn appropriately. So everything is inverted. So this being pointed down means it's actually pointed up, so it would be beta. I'm not going to ask you that on a test. It's confusing, I know, but I want you to look at some variations here. What actually happened to carbon number 6 of fucose? It's just CH3. It looks like it's lost its OH. It's been removed, right? So it's been reduced. Look at the middle two. Their carbon number 2 doesn't have an OH on it anymore. It's got an amino group, right? It's got a nitrogen pointed down. And on the amino group has actually been an acetate group that's added, much like our histones had an acetate group added, right? So they're not just sugar anymore. So if you look at this one, carbon number 2's OH, what was originally an OH, was down. Number 3 was up, and number 4 was up. What sugar did this start out life as? So 2's down, 3's up, 4's up. So I'll give you a hint. Look at the other one. 2 down, 3 up, 4 down. That's glucose. So down, up, down. That's glucose. Here we have down, up, up. The only change is at number 4. If you remember back from our other slide, the only change at number 4 from glucose means it's galactose. Right? So this is galactose, and this one over here is glucose. I've also changed the OH at number 2. It's not an OH anymore. It's an amino group, so it's not glucose, it's glucosamine. And then I've added an acetate group to it. Right? So it's acetylglucosamine. Right? And more specifically, you should say it's on number 2. Whereas this one's acetylgalactosamine. Right? If you look on the bottom, we have glucose 6-phosphate. That's the one we just described. This number 6 has a phosphate group attached. Whereas on the one on the far right at the bottom is our 3-carbon dihydroxyacetone, and I've added a phosphate to its carbon number 1. So it's dihydroxyacetone phosphate. Okay, so lots of modifications. The sialic acid's another example where we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. That's a really long. So carbon number 1, 2, 3, 4, 5. It's been changed from an OH to an amino group. So it's instead of a normal sugar, it's now an amino sugar. And again, I've added an acetate group. Right? So we give it the name sialic acid because we didn't want to name it by its acetyl neuraminidate all the time. Okay. So, all right. Do you want to hear a funny story about an enzyme? Helps you remember some of this.
Yes.
Yes, please.
Okay. So, I was told the story when I was in graduate school or undergrad, or I don't remember, one of those, by the person teaching me a biochemistry course. And you don't want to write out glucose and galactose and mannose and all these names all the time, dihydroxyacetone. We use abbreviations, right? So the abbreviation for glucose, as you see in the middle of the screen here, is just GLC, glucose, GLC. Galactose is GAL, right? And you can imagine ribose is RIB, right? Or you can imagine mannose is MAN, right? So we use three-letter short abbreviations to name all these sugars. And if you were an enzyme, and your job is to put a phosphate on something, that class of enzyme is a transferase, and more specifically, it transfers phosphates. We call them kinases, right? So enzymes that transfer things are called transferases, and if it transfers a phosphate, we call it a kinase. So if you were an enzyme that transfers phosphates onto, say, galactose, right? Your job is to put a phosphate on a galactose. You would be called a galactose kinase. If your job was to put a phosphate on a glucose, you might be called glucose kinase. Well, you wouldn't want to write glucose kinase and galactose kinase that many times. So you abbreviate it. So say for a glucose kinase, you might write GLC, capital G, little l, little c, and then a capital K after it for kinase to abbreviate the name of it. So it'd be GLC, capital K. We'd read that as that's a glucose kinase. A mannose kinase would be capital M, lower a, lower n, capital K, mannose kinase. So back in 1988, a group at Harvard published a paper, and they were working on the sugar on the far left of your screen, and they were working on the enzyme that puts phosphates on that sugar. And you can imagine the abbreviation they would use following those rules. Right? So they worked on the sugar fucose, and they were working on the enzyme that puts the phosphate on it, fucose kinase, and they published this paper. And if you look all throughout the paper, unknowingly, they were using an abbreviation that doesn't work too well. Right? Now, don't blame the authors, because based on their names, English may not have been their first language. Right? And of course, when it was submitted to the Journal of Bacteriology, you see at the top, in 1988, and it came from Harvard, so not many people really questioned it. I do blame Allison. Right? So I think some of the blame here lies with Allison, because they like to thank Allison Ulrich for her editorial assistance, and based on her name, I suspect she speaks English. So you would not want to use this abbreviation throughout this paper, and it occurs dozens of times throughout the paper. So be careful what abbreviations you come up with, and of course we don't use that one anymore today because of this paper. Right. Okay, so now let's move on. Instead of looking at single sugars, we're going to talk about putting these sugars together, like the one I just described. We put one sugar on another. We're going to learn several disaccharides, which is two sugars put together. And the easiest and simplest one is just make it from pure glucose. So I'm going to take two glucose molecules and put them together like you see at the top. So I have, first one is alpha glucose. How do I know it's glucose? I look at numbers 2 down, 3 up, 4 down, or right, left, right. That's glucose. And it happens to be on number 1 down, so that's alpha glucose. Then the other sugar to which I'm attaching it happens to also be a glucose. Number 2 down, 3 up, 4 down. Right? It says alpha on the right, but that's irrelevant because it's not involved. This could have been beta. It doesn't make any difference. I still get the same connection. But this one had to be alpha. So the connection tells me that. It's an alpha 1 connected to a 4. Right? So alpha tells me number 1 is down. And because I know this is glucose, I don't have to tell you anything about number 4. I know it's down. If it were not, it would not be glucose. If this were an alpha 1,4 between a glucose and a galactose, that 4 would be up, and it would not be maltose. Okay, so maltose is a disaccharide made from two glucose molecules, where the first one must have been in the alpha form, second one's irrelevant, what form it's in, and the connection is between number 1 and number 4. So we call it an alpha 1,4 glycosidic bond or glycosidic linkage. Right? There's lots of others we're going to go over, but you get the idea. I named the first sugar, I named the second sugar, and I tell you the connection. So maltose is a disaccharide from a glucose and a glucose, where the first one must have been in its alpha form, second one didn't matter, and it's an alpha 1,4 connection. Another example, this is what I was talking about earlier, and it was ideally a transferase. I want to put something on another sugar, right? X being whatever it might be. It could be another sugar as shown in the bottom, right? So I take X and I take this sugar, which has been activated by attaching it to some other group. In this case, a UDP molecule, right? A uridine diphosphate. This connection here is very unstable, right? The sugar wants to leave, much like the third phosphate wanted to leave when we made this, right? So the sugar, the UDP separates from the sugar, the X goes on the sugar, and the H goes with the UDP to leave as UDP, right? So here we have X attached to the sugar. X could be anything. It could be another sugar in the case of glycogen metabolism. And we'll cover that when we get to that in metabolism. Okay. The other disaccharides I want you to know are lactose and sucrose. Okay, so lactose is shown on the top left. Here we have a sugar number 1 and sugar number 2 in this order. It's very specific. Sugar number 1 here is what sugar? Right, so we have 1, 2, 3, 4, 5, 6 carbons. We have number 2 is down, number 3 up, and number 4 up. So what is this sugar?
Galactose?
It's galactose, correct. So down, up, down would be glucose. And the only difference here is we switch number 4. That's how we make galactose. So it's down, up, up. That's galactose. And is galactose in its alpha or beta ring form?
Beta.
It's beta because I look at carbon new chiral center, right? In this case it's number 1, and it's pointed up. Okay. Our second sugar over here is what? We have down, up, down.
Glucose.
Yes, it's glucose. And is it alpha or beta in this drawing?
Beta.
Happens to be beta, but it didn't have to be. It could have been alpha. That's irrelevant. You notice this carbon is not involved, or this carbon's OH is not involved in the connection. So it's irrelevant whether this side was alpha or beta. So we have a galactose and a glucose, and the connection was again between numbers 1 and 4, but this one happened to be beta. So if I do a beta 1,4 connection between a galactose and a glucose in that order, I get lactose, or a milk sugar. Okay. And the third one I want you to know, we did maltose, lactose. The third one is sucrose. This is table sugar. Okay, here we're going to start with 2 molecules again. We're going to make a disaccharide. And in this case, both of them matter, whether they're alpha or beta. We're going to use a glucose at the top, and you probably could confirm this is glucose. We could look at down, up, down. That's glucose. And number 1 is down, so it's alpha, and that matters here. And in the second one, we have fructose. And if you look at it, number 2 is the new chiral center, right? Number 1 was not chiral because this was a ketose. Number 2 is the new chiral center. It wasn't before, it is now. The OH is pointed up, so it's beta. Then we have number 3 up and number 4 down. So like glucose, 3 up, 4 down, this is fructose. Okay? You notice numbers 2, 3, and 4 are not in the same positions they were as in glucose, because this is a ketose. Remember, the attack occurs at the carbonyl. It's not at number 1 in this case. It's at number 2. So I have a alpha D-glucose and a beta D-fructose. Okay? And number 1 of this one is going to combine with number 2's OH of this one, right? This number 1 up here should actually be written on the carbon down here. I don't know why they put it up there, but this 1 should be written down here on the carbon. But this OH pointed up from number 2 and the OH pointed down from number 1 are going to interact and form a new bond. There are no additional carbons added, and I know a lot of diagrams will show it with a bunch of extra bonds, and that's not, I hated that because it's not true. But there's a connection here that retains their up and down identities, right? So the bond here is an alpha 1 and beta 2 glycosidic bond. So sometimes it's written alpha 1 beta 2, sometimes you'll see it written as alpha beta 1 2 respectively. So alpha with the 1, beta with the 2. Right, so it's glucose in its alpha form, fructose in its beta form, number 1 of the glucose and number 2 of the fructose, alpha on the first one, beta on the second, forming sucrose. Okay, and sucrose is unique among these three. So let's go back to maltose real quick. If you notice, when I make maltose, I close the first ring, I fuse it shut. There's no OH anymore here. I can't open this ring. It is no longer a reducing sugar. However, the other sugar, the other glucose here, can still open and close at will. So maltose will still behave as a reducing sugar. It'll give you that brick red or the silver mirror in the Tollens test. If we look at lactose, the second sugar can still open and close, right? Its new chiral center is available. It can deprotonate and form a carbonyl again, so lactose will again test positive. However, sucrose, since I involved both new chiral centers in this connection, both rings no longer have an OH here. And so both rings are fused shut. So sucrose will not test positive, right? So it will not change forms from an alpha to a beta or a beta to an alpha if you heat it up, which is why sucrose, or table sugar, is excellent for making things by heating it, right? You can't make hard candy, they can't make consistent hard candy out of lactose or maltose. But you can from sucrose because you can heat and cool it as many times as you like and it's the same molecule. It's not going to become a 50-50 arrangement like the others will. Okay, so sucrose will not behave as a reducing sugar. It will never give you that brick red color. Okay, so those are disaccharides, only 2 sugars, so I want you to know those 3. And then we're going to go over some others that are polysaccharides. So this is not just a couple sugars, this is many, many hundreds of sugars, right, put together. So one example of that is glycogen. Right, another name for glycogen is starch, depending on its source. We generally call it glycogen if it's from an animal, from a liver or a muscle cell or something like that. And we call it starch if we get it from a plant, right, from the plant cells. So what glycogen or starch is just a polymer of glucose. It's basically maltose. I just keep going, right? Instead of just having 2, I add a third and a fourth and a fifth and 6th and so forth, and I make this long chain. Every bond here is still alpha 1,4. Right? So every one of these molecules is completely the same, right? All alpha 1,4 glucose. Occasionally, instead of having a bunch of long strands like this, I branch off and I make an alpha 1,6 connection. Right? So if I look back, here's my alpha 1,4. If you imagine this repeating over and over and over on the screen, occasionally I'll branch off one off a number 6. And then I have a new chain I can extend many, many times, right? And I can do this at many points and get a nice branch network. And that makes the polymer, the polysaccharide glycogen or starch, able to take up less space and to occupy the cell without being a bunch of long, thin spaghetti strands, right? It also makes it a little more compact, but a lot less soluble. Right, so once it starts getting huge, this precipitates out in the cell. Basically, we just sweep it into a closet, store it for later until the cell needs more sugar. We can break this down. Okay. Here's some other polymers we can look at. We have glucosamine and galactosamine at the top, where one of the OHs has been replaced by an amino group. Right, very simple. This is much like our arrangement from earlier. We can have something called heparin, right, in the middle row on the right. A lot of the R groups, but a lot of the OH groups have been heavily modified. Some have been sulfated, some have been oxidized to a carboxylate, some have turned into a nitrogen and then sulfated. So the thing I don't like about these figures is they show the connection between the sugars with all this angled carbons. There are no carbons here. What they're trying to show is that the O is up from the first sugar and down from the second. And that's a terrible way to explain this because there aren't 4 additional carbons. They're just being lazy in the way they draw it, but also they want to put it all in one row on this table. A better way to draw heparin would be to draw it in the way I drew lactose over here. Whereas this one's up and this one's down, they're not in line with each other. One is above and slightly to the right of the other. It clearly shows the arrangements in the two. And there's no extra carbons, right? Same thing with these two. But they tend to do it this way, or you look at the bottom, it gets really odd when you have these 1,3 connections and so forth. Okay, but lots of modifications to sugars can be made, right? And these modifications give the sugar other properties, right? So these glucosamines, galactosamines, chondroitin sulfates, dermatan sulfates, and all, the hyaluronic acid at the bottom, these are used as lubricants in joints. Okay? Heparin is used as we call it a blood thinner. It's a misnomer. It doesn't thin your blood. It just prevents or decreases the chance of coagulation. It inhibits a factor in your coagulation pathway. And also the shells of insects, right, or crustaceans, are made of polymers of sugars, right? And we call it chitin, right? It's a glycosaminoglycan, which means it's a sugar attached with an amino group to other sugars and proteins to make these hard shells for insects and for crustaceans and other organisms. Right, so we can also take our sugars and attach them to proteins, right? We don't have to attach it to simply other sugars. So if we attach a sugar to a protein, so shown in this really weird drawing here is this protein backbone and the zigzag green here, and one of the amino acid side chains is shown. Which amino acid is this? Which amino acid is shown off of this backbone right here in the center? It's 2 carbons long and an amide. The amide alone should narrow it to 2 choices. So don't forget your amino acids. This is not a test dump and then you don't have to remember it again. We're going to use them all over again. So this is one of your 2 amide R groups. It's the shorter of the 2. This is asparagine, not glutamine. Right? And to it, I've attached a sugar, whatever sugar this might be. Right? It's not hard to tell in the drawing because it could be a bunch of them. But we've attached the sugar through the same linkage, except instead of being alpha 1 something, like 2 or 4, it's alpha 2 amino group. Right? So I've attached the sugar through this amino group. I can also attach it through an oxygen. So on the right here, I have a protein backbone again. And this is a different R group. This happens to be threonine, right? And I'm attaching the sugar through the OH of threonine. So we call the first one a CN glycoprotein linkage or glycosidic bond, and the next one on the right a CO glycosidic linkage. But they're both attaching a carbohydrate to an amino acid of a protein. Right, so these are called glycoproteins because they're sugars attached to proteins, or if you want to think of it the other way around, I've attached a protein to a sugar. Either way you want to think about it. And an example on the cell, so here's the cell membrane on the left. We have a protein that's embedded in the membrane, and attached to its surface are several sugars, shown in the little hexagons here. Right? And what's the point of all this? Well, we can have cells with different proteins on its surface, and on those proteins are attached sugar trees, and the sugars can vary wildly. There's glucose, and mannose, and fucose, and ribose, and all sorts of sugars. And we can combine them in many different ways, and basically gives a fingerprint to the surface of the cell. What's the point of that? Is so cells can find other cells and tell them apart. Your immune system takes advantage of this. Your immune system roams around, walks up to a cell, doesn't have legs, but walks up to a cell and says, show me your papers, basically, right? So it tastes the outside of the cell. There's a receptor. It says you have the right sugar tree here, you belong here, you're a muscle cell, I'll leave you alone. Right? But if you can't prove who you are, the immune system will say, you don't belong here, and attack it, right? If it's a bacterial cell, for instance, or a yeast cell or something like that, it doesn't belong there. If it doesn't have the right sugar trees, right? Sometimes those immune cells make a mistake and they attack a cell that's supposed to be there. Those are autoimmune diseases. Okay. The other example is the fish on the right. So Atlantic codfish and most North Atlantic fish in general, they can survive in these waters. The waters are actually below the freezing point of pure water. But the water is not frozen, number one, because it's a huge bulk of water and is constantly in motion in the oceans. And of course, it's got salt in it, which lowers the freezing point. Right? But these fish, if they didn't have this protein, their cells would freeze. So they have these proteins that are proteins with sugars on them that act as antifreeze in their blood. Right? So without this, their blood would freeze. Okay. Right, so another example of these proteins on cell surfaces that basically show me your paper, show me what kind of cell you are, is our determination of blood type. Right? So you can have lots of different sugars attached, and some examples are at the bottom, right? Or many different types of sugars. But I want to bring your attention to one in example, and that's how we determine our ABO blood groups. We're not talking about the RH factors or plus or minus. That's a different group altogether, a totally different sugar tree. But we're going to talk about the simple A versus B versus O blood group. So in that example, the normal, what we consider normal, is the A antigen, right? So the enzyme assembles this tree. It puts galactose on at the bottom, and then it puts an N-acetylglucose on top of that, and then a galactose on top of that, a fucose off to the left with a 1,2 linkage, and then yet another N-acetylgalactose off to the right with a 1,3 linkage. That's your normal sugar tree on an A-type cell. That enzyme that puts that last sugar on, the one that's the dotted box here, or the dashed box, that enzyme sometimes has a mutation where it puts on regular old galactose instead of the N-acetyl version of galactose. And we call that the B antigen. Sometimes that enzyme has a mutation or one or more mutations that make it non-functional altogether, and it doesn't put any sugar on there. We call that the O antigen, right? And so depending on which of these genes you inherit from your parents, you could have one that's normally functioning and puts the N-acetylgalactose on, and the other version might do the same thing, and that would be an AA genotype. You could get one that puts the N-acetylgalactose version on and one that puts the galactose version on from your other parent, and you could be an AB genotype. You could inherit one that puts just the galactose on, B, from one parent, and one that's non-functional from the other parent. Then you would have the BO genotype. Phenotypically, it would look like B, because the one that's functional would do its job. The one that's non-functional clearly doesn't. So the only way to get the O phenotype in this scenario is to have two non-functional genes you inherit from the parents. So an O and an O is the only way to get that. So this is how we have our three different, in general, blood types, A, B, and O. But you can get an AB if you get one A from one parent and one B from the other. And the last thing I want to say for this lecture is these sugar trees on the surface are also used by other cells, not just our immune cells, but other things like virus particles. Right? So these virus particles usually have a nucleic acid genome in the center, RNA or DNA, and many of them are covered in a protein coat. And on the surface of that protein, they have other proteins sticking off. Right? Some of them even have lipid layers around them. And embedded in their lipid layers are amino acids of proteins that stick out. Okay, so one example of that is the influenza virus here shown at the bottom. And influenza has many types. You've probably heard of different types of influenza virus. And what it does, it's a respiratory virus. And the little things that are sticking off the surface recognized as sugar trees that occur on lung cells. Right? They don't occur on any other cell type. It's looking for that particular cell type because it has the right tree on the surface. So it's called viral or cell tropism. It's looking for a certain tree type, right? Sugar tree. And so what it does is it recognizes it using this molecule called hemagglutinin, right? So that's the little stick figure shown there. It recognizes the host cell sugar tree and binds to it. Now the virus has the issue of getting its genome, it's 8 strands of DNA in there for their influenza virus, from the virus particle across both of these membranes and into the cell. Well, it's hard to cross these membranes, and we also have no way to fuse the membranes at the moment because all these proteins are in the way. So if we could only just chop down all the trees, then this would work. So the virus also has an axe on its surface. This is the neuraminidase, shown as the little bulbous tree. Right? So it has an axe on its surface that chops all these trees apart, right, after we've made a connection, pulls the two membranes together, they partially fuse, and the DNA or RNA can get through there into the cell. Okay? So this is why you hear of it when you have like H1N1 flu. They're referring to the hemagglutinin, the H, and the neuraminidase, the N, the type of proteins on its surface. Those can mutate wildly, right? So when you have a specific immune cell that recognizes a certain hemagglutinin or a certain neuraminidase and says, hey, you're that flu we saw 20 years ago, right? Or in your case, 2 years ago, right? And you recognize it and immediately get rid of it. You don't even know you were infected by it. However, the virus mutates all the time, right? And it makes a different hemagglutinin, serves the same purpose, but it has a slightly different look. And the old immune cell doesn't recognize it anymore, and you can get sick from the new flu strain. Right? So H1N1 is an example, H1N5, and so forth. There's lots of H's and N's in a combination. That's why there's so many flu strains. Right? And what we do each year is whatever is occurring, let's say in Australia, South Africa, Argentina, and Chile in the southern hemisphere, right? Those are the major population centers. Whatever flu strain is dominant during their winter, which is our summer right now, is we're going to try to make a vaccine for the most dominant ones that we're likely to encounter this fall, right? Because of global travel. And if they guess correctly and everyone gets the vaccine, or at least like 80% of the population due to herd immunity, then we have a very mild flu season, we call it. Not many people get sick. If they guess incorrectly and don't have the most common one that actually shows up, then everyone suddenly gets the flu. But they had the vaccine, but it was a poor guess, right? So it's always a guess. We try to get the most common ones. I mean, I don't do it, but people at the CDC and other places do. And if they guess correctly, then you have a very mild flu season. But it's only true if the herd immunity has gotten the vaccine.